How did I come up with those folding numbers in the first place? So for this, we are going to take a step back and look at what the original biquad filter structure looked like, and not the form in which I showed it to you just now. Okay? What I mean is, the normal biquad filter structure that would be familiar to a person from the signal processing background would look something like this. Right? This is essentially a second order or basically a biquad filter structure, right? It has two components. It has an IIR component as well as an FIR component. How did we obtain this? It essentially comes up from the structure of the normal, the y of n is equal to something y of n minus 1 plus something y of n minus 2 plus something x of n minus 1 plus something x of n minus 2, right? But if you look at it, it's a bit more tricky than that, because what has happened over here is the IIR portion, the feedback, is in the left hand side, the earlier part of the diagram, and the feed forward is in the later part, right? It turns out that this is most easy to understand if you look at it in terms of the signal flow graph and do that transposition operation that I had mentioned somewhere in the earlier when we were talking about signal flow graphs, right? That's the easiest way to sort of obtain this structure, right? But how we obtain it, why it works, why it is used, etc., is not our concern. As far as we are concerned, the reason why we take it up is, A, it is a very common structure in several kinds of signal processing applications, primarily related to speech and other kind of things, but also it has certain properties that make it a very stable and useful basic component of signal processing hardware implementations, right? And as far as we are concerned, it gives us a very nice simple structure that allows us to experiment with different kinds of, or rather allows us to understand the different kinds of scheduling algorithms easily. Okay. So once again, I am just going to label these nodes 1, 2, 3, 4, 5, 6, 7, 8. And you can see that the difference between this and the diagram that we used earlier is simply this: the positions of those delay elements or registers is different. Okay. Why did I have to make those changes? Why those specific positions? Were they important, or could I just have placed them anywhere? That's what we are trying to understand now. So to figure this out and to sort of see how do I come up with a schedule, right? We would like to essentially understand what are the real dependencies that I have over here, and how would I systematically go about constructing a possible schedule of operations on limited amounts of hardware, if I had to do that. Okay. So what am I dealing with? Let's take a look at this. Based on what I have over here, right, I am just going to ask a few questions. Let's say that n is equal to 4 as before. Okay. The question that I am going to ask is 0 acceptable as a scheduling time instant for operation number 1? Or, I mean, so what would you say if I asked you that? Is 0 acceptable as a scheduling time instant for operation number 1 as it stands right now? No. Why? Because there is a dependency from 3 to 1. Therefore, 3 has to complete before 1 can execute. There are no delays on the edge between 3 to 1. That's all that I care about, right? I only care about the edge between 3 to 1 right now. There are no delays on that edge. Therefore, the only possible way that 1 could execute at time 0 is that 3 has a negative schedule instant, which is not possible. Okay. This would force operation 3 to execute at negative time. Okay. So clearly 0 is not possible. The next question I can ask is 1 possible? At least the if operation 1 is to execute at time instant 1, what would that imply for operation 3? It has to be at 0. What does that imply for operation 5? It would have to be negative, which again is not possible. Okay. So therefore 1 is also not okay, because this would imply 0, this would imply this becomes negative. So that's also not okay. Now what about operation 5 executing at time 0? Is that okay? Do you see any problem with operation 5 executing at time 0? Operation 2 would have a problem. Okay. So now what would, let's work through this, right? If operation 5 is scheduled at t equal to 0, what would it mean? Operation 3 has to be at t equal to, it has to wait till 5 completes, and 5 is a multiplication. So the latency of multiplication is 2 clock cycles, 2. That's the earliest time that operation 3 can execute. I should put greater than or equal to, but I am just going to put equal to over here. Operation 1 therefore can execute at time 3, right, which in turn means operation 2 at time 4, and this is a problem. This is not possible if n is equal to 4. Okay. And in fact, this is raising a fundamental problem for us, because if I really look at it, what is happening over here is, there is a path that leads over here which has a length, a total delay length of 2 plus 1 plus 1 plus 1, 5 time units. So there is fundamentally no way that I can get everything to finish within 4 clock cycles with this arrangement. Okay. And in fact, what is the name that I normally give to this path? The critical path, right? What it's saying is, in this diagram as it stands over here, the critical path is 5 time units long. So n equal to 4 is basically not possible, since the critical path is equal to 5 time units. Okay. So what do we do? Let's assume n equal to 5. Okay. So what does this correspond to? I am just going to put down a time chart over here, right, where I put t is equal to 0, 1, 2, 3 and 4, and put down the operations over here, right. Let's go back and look at this. What I can see is operation 5 can be run at time equal to 0, no problem with that. That would imply operation 3 can be at time 2. Okay, so I am going to put an arrow between them to indicate that there is a dependency over here. Operation 1 at time 3 and operation 2 at time 4. What about the rest of my dependencies? So that is basically, that has taken care of this path 5, 3, 1, 2. Okay, all right. What about operation 6? That can also execute at time 0. That in turn feeds into operation number 4, and that in turn feeds into operation number 2. What about the other operations? So I have 7, which again feeds into 3. Okay, so the output of 7 again has no input dependencies because it has a delay element in front of it. So what that basically means is, anything which has a delay element in front of it, the input corresponding to that could have executed in the previous iteration. Okay, so in this particular block, the schedule that I am trying to put down for these 5 phases, right, 5 has no dependencies, 6 has no dependencies, 7 has no input dependencies, and 8 has no input dependencies. okay. And if you look through it, what you will find is 7 is also here, 8 is over here, okay. This is the set of dependencies that I have got right now, okay. What you can see from this is this or this, either one of those is a critical path. Right, whereas this one over here is not a critical path, okay. So you see the difference between those two paths, the 642 and the 842 also terminate on 2, but they are not critical, in the sense that the output of 4 was ready by time 3, okay. So how does that help us? Potentially what I could have done is to have a slightly different schedule, which could have given me, which could have basically allowed me to sort of push this down. So 6, in other words, could have gone here, 8 could have gone here, and 4 could have gone here, and I would have still met my timing constraint. Okay. So the paths that are not directly on the nodes that are not directly on the critical path, in other words, could be moved around a little bit. Okay. I am anticipating a little bit over here. This is essentially the same as the concept of slack in a digital combinational circuit, right. There is some slack on this path, whereas on the 5312 path or the 7312 path, there is no slack. They are exactly critical. The others have slack, they have some amount of mobility, okay. So how does this help us? If I was to say n is equal to 5, let us go one step further and say, is that good enough? If I just said n is equal to 5, now can I get a hardware architecture where I can just use one multiplier and one adder and get all my operations done? Yes or no? Will I be able to manage with one multiplier and one adder? Still not going to work, because I have two multipliers sitting at time instant 0 on my critical path. They can't be moved. In my original schedule, of course, the one that is written in black, 5, 7, 6 and 8, all the multipliers are scheduled at time 0. The only way I can do that is use 4 separate multipliers. Okay. So as things stand right now, with my original schedule, 5, 6, 7, 8 are all scheduled at time 0, I need 4 multipliers.